please put your microphones on mute. Okay. So that's the first request, so that we don't disturb the speakers in between unless you have questions to ask. Okay. So welcome you all for this asset colloquium, and today I am substituting Satya because Satya is in Pune, and I'm sure he must be there online available. Okay. So the asset stands for Advances in Science, Engineering and Technology. The Asset Forum conducts colloquia under the broad spectrum of fields covered by asset. Apart from TIFR colleagues, eminent speakers from outside are also invited to give talks in this forum. These colloquia are held at 4 p.m. on Friday, and they are complementing the other two at the TIFR, namely the NSF colloquium on Wednesday and mathematics colloquium on Thursdays. Now today we have two speakers, Professor Gagan Mohanty and Mr. K. Kameshwar, both from Department of High Energy Physics of TIFR Mumbai. Professor Mohanty works at the particle physics frontier, understanding the fabric of our universe via research for effects beyond the standard model. He is an internationally recognized leader in heavy flavor physics. As physics coordinator of BEL, he steered many physics analysis to maturity that include BMS sensitive papers on charge parity violation and rare decay structures. In BEL 2, Professor Mohanty led the TIFR effort in building a sophisticated silicon-based detector, the first in India to measure the decay, vortex, and charge particle momentum. Mr. Kameshwar, a BTech in electronics and communication engineering from Nagarjuna University, Andhra Pradesh, joined TIFR in 1996 for the Gamma Ray Observatory in Panchmari, Madhya Pradesh. Later, he moved to the DHEP group, Mumbai, around 2005, in order to work on the design, development, and characterization of silicon microstrip detectors in collaboration with Bharat Electronics Limited. During the last several years, he has been significantly involved in the assembly of the silicon voltage detector for the BEL 2, and very recently the design and prototyping of CMS high granularity calorimeter. Now today's colloquium is about these two detectors or these two efforts. One is silicon strip voltage detector, which is SVD, at the BEL experiment at KEK, and high granularity calorimeter at the CMS experiment. So I request both the speakers. So to begin with, Professor Mohanty, to start with.
So anyway, I will take about 10 minutes, and so mostly target. So okay, so title of the colloquium is From Ladders to Cassettes. So this is basically the two activities that the Vaibhav said. Our report on the silicon vortex detector for BEL 2, and this high calorimeter calorimeter, another silicon-based detector for CMS experiment. So as I said, I will talk of the scientific aspect of that, and then Kamesh will talk of more on the engineering and the real building stuff. So, so here is the outline. I speak for maybe 10 minutes on the introduction on the scientific part of this experiment, and then Kamesh will cover the part on the BEL 2 silicon vortex detector and HGCAL. HGCAL is a very preliminary stage we are in right now on the designing and prototyping phase, and then summary. So as far as the question answer part, so sort of we will take on if there is some question like that concerns the science part. I may step in, otherwise Kameshwar will discuss. So we will take it together. So the first thing is, I mean, just more for the benefit of the student and for the people at large. So where do we stand? So this is the kind of state of art particle physics where today. As you know that there are, the ordinary matter made up of proton and neutron and electron, proton, neutron making the nucleus and the electron. And as we see the proton, neutron, they are not elementary object. I mean, they're not elementary particles. They are made up of the quarks. These quarks are held together by this strong interacting messenger particle called gluon, that forming the nucleon, and then the nucleon forming the nucleus, and then you have sort of the electromagnetic interaction like the nucleus and the electron forming the atom, and then you go into molecules. So that's why. So what we know, ordinary matter is mostly made up of, not mostly, it is made up of the particle belonging to the first generation of quark and the lepton. But then you have these two exotic, sort of more massive counterpart for the quarks and lepton. So there are 6 quarks and the 6 lepton, and these are so-called the gauge boson. They are spin-one particle. They are mediator of the different interaction we have. And then you have this so-called the Higgs boson. So this is a special kind of particle, which is in a sense we can say mass enabler. So how do we have the mass in this particular particle physics framework, what we call standard model? And now, this is what some our theory colleagues, they write the entire theory of standard model, what we call in this so-called the Lagrangian of the standard model that you see very elegantly expressed here. Like the various term you have, and that's exactly what you see, the quarks and the lepton and the interaction of the gauge boson with the quarks and the lepton and the Higgs, the so-called the HGCAL coupling, the Higgs interacting with the fermion and the Higgs through the spontaneous symmetry making, giving the mass to this gauge boson. So this is where we are right now. That standard model is a successfully, is a successful theoretical framework, which is we have arrived at by this successful marriage between theory and experiment. And so in order to get to this story of standard model, it has been built on, there are several, instrumentation have played a key role in this work or the development of the standard model. So I will take a few specific examples. The first example I would like to take the so-called silicon vortex tracker for the Babur experiment, which essentially was key to prove that there is so-called the CP violation or matter-antimatter asymmetry in this B meson decay. Without understanding this plot in greater detail, if you see that the B meson and the B bar meson, the antiparticle of B meson is a subatomic particle made up of a B quark that I introduced in the previous slide and another kind of quark, in this particular case a D quark. And what you see, if CP violation wouldn't have been there, both the blue and red, they would have been on top of each other. And the fact you see CP violation is there is a clear distinction between the matter and antimatter, and it's very nicely following the sinusoidal curve, and that very much consistent with the standard model. In order to enable this kind of Nobel Prize winning discovery, and because of this discovery, Kobayashi and Masukawa, they shared 50% of the Nobel Prize in physics. So that was mostly done by the silicon vortex tracker, because you want to identify this B meson. Those are produced at this E plus E minus interaction point, but they decay at certain distance, and you need to very precisely locate their decay vortex position. And for that, you need silicon tracker. The second example I would like to give is so-called the Higgs boson. So this is a very special particle in the standard model, and this was discovered by the 2 experiments at LSC, so-called Atlas and CMS experiment. Here you see a plot of, again, you don't have to worry about the nitty-gritty detail, but what you see that if you look at the diphoton, there's a 2-photon invariant mass. You are looking at the sort of, you take the energy momentum of the photon, and then you find out the invariant mass. So what you see that there is a very much what we call continuum background, and you see a very nice peak here at 125 GeV observed by both Atlas and CMS experiment. And not only in the so-called the diphoton mode, there is the so-called the 4 lepton mode. And there you clearly see this one, by the way, this is a Z boson peaking around something like 91 GeV, and you see a peak at 125, 26 GeV. So the fact, this kind of very beautiful picture you see, that is also made possible by this, particularly for the diphoton, there was this very beautiful electromagnetic calorimeter for CMS, that's so-called lead tungsten crystal calorimeter. And then again, CMS had this 10 layer of silicon strip detector, which was very, very crucial even for diphoton thing, because the diphoton of photon being neutral particle, in order to identify from which particular vertex the diphoton comes, you need to sort of study the properties of the other particle, and that was done by the tracker and the pixel and the strip tracker. And again, we talk of the 4 lepton, in order to measure their momentum very precisely, you need the silicon tracker. And very recently in the LSCB detector, I thought I will show these two beautiful plots. So in this plot, what you see the capability of this tracker. If your silicon vertex detector does not have that kind of precision, what you will see, that is what you are seeing here, there is a particle antiparticle oscillation. So there is what we call, so there is a B quad and the strain quad making a B sub S meson. And this is what we call B sub S bar oscillation. This is predicted by the standard model. Now, if you don't have a detector which is able to identify lifetime to the precision of that picosecond, what you will be seeing, you will see just a curve, right? Without seeing that there is a kind of up and down. So in order to see that, you need to have a time resolution of few picosecond, and that was enabled by this so-called vertex locator by LSCB experiment. And the other aspect, the very highlighted result from LSCB, where they are finding, so if the standard model is correct, that here, in this particular plot, you are basically plotting the ratio of some two decay branching fraction of B meson. And if standard model is true, the ratio should be consistent with 1. And what you see that LSCB has measured something over here with the uncertainty of this, which is about 3 to 3.5 sigma away from the standard model. Now, whether that is new physics or not, that's something we have to see with more and more data. But again, for LSCB, whatever physics deliverable LSCB has got so far, one of the key components for the LSCB detector is so-called the veloric vertex locator or silicon strip detector. So the standard model story is essentially complete with the discovery of the Higgs boson. All right, but then we know that standard model cannot be full story. There are several pressing questions that standard model cannot address. For example, in the standard model, there are only 3 interactions, 3 fundamental interactions are part of standard model. Maybe strong interaction, weak interaction, and electromagnetic interaction. So gravity stays outside the realm of standard model, number 1. Number 2, in the standard model, neutrinos are massless, but by now we know that they do have mass, therefore they oscillate, so-called the neutrino oscillation. The number 3, from more like cosmological consideration, what we know in terms of standard model particle or so-called baryonic matter, they comprise only 5% of the total matter energy density of the universe. So there is dark matter, dark energy. Of course, some of my colleagues, they don't trust dark matter, but there is an alternative theory of gravity. But let's say that we understand 5% of the total matter energy density. What is that 25 or 75%, 25% matter or 70% dark energy? That we do not know, and there has to be particle interpretation for that, particularly for the dark matter. And also the CP violation that I showed in plot, there is also like what we see in the universe, the so-called the baryon asymmetry, cannot be fully explained by the smallness of the CP violation that we have in the standard model. So these are the 4 pressing problems that standard model cannot solve. But of course, there's many other things like why Higgs boson is so light, why the top quark is so massive, and there is a large diversity in the mass range. So those are the questions, broad questions that standard model is not able to answer. We don't have a clear-cut sign, I can say, for new physics. So the stage right now where the field is, we need more and more precise measurement of, I picked up these of the particle, for example, the Higgs boson. This is for the first time we have a scalar particle which is elementary, which is point-like particle. We have lots of scalar particles, but they are all what we call composite particles, like all the meson, pion, kaon that you all know, the scalar particle. But this is the first time you have something presumably elementary particle. Then the top quark, this is, you can see already RGB as like tungsten atom. So we need to precisely measure the top quark, various properties of the top quark. The big quark, there's something very close to my heart. I mean, this Bell 2 or LSCB experiment, they're going to do that, or LSCB is doing. And also CMS Atlas slowly, ramping up their physics program for this in order to see that the flavor anomaly we talked about. And of course, neutrino, there is many measurement that you can do with neutrino. So in order to sort of build up the case, I mean, in order to see how we go beyond standard model. So Bell 2 is one such experiment where you are not going to very high energy. Like for LSC, we're talking of right now 13 tera electron volt, which will go to 14 tera electron volt. So there you have access to sort of new particle which can be of the mass scale of few TeV. Of course, in Bell 2, we don't go to that kind of energy. We are talking of energy of 10 GeV, so 3 order of magnitude lower than what LSC is operating. But the fact is, it's a E plus E minus factory. You have a cleaner, much cleaner environment, and that experiment is ideally posed to probe what we call new physics. So you are going on to much higher intensity or higher luminosity. And in this particular, the way Bell 2 will probe new physics is an indirect way, what we call, because you are looking for some decay processes which are very rare or suppressed in the standard model. And if you have a new physics contribution, that will disturb the kind of the prediction of the, what you measure in the experiment. And that, in order to do that, again, silicon vortex detector will play a key role. And you can see in this plot that how much the kind of impact parameter. So by the way, we are talking about 15 micron vortex resolution, right? So that just to give you a scale, your hair size is of the order of 50 to 100 micron. So that is the level of impact parameter you are able to pin down, which is sort of twice better than what Bell and Babur experiment had achieved. And then the other one I would like to say, and that is going to be the case for the so-called high granularity calorimeter for CMS. This is for the first time you have a silicon-based calorimeter. All this experiment I told about Babur, Bell, Bell 2, LSCB, CMS, all of them had silicon tracker. So silicon is very well known for measuring the charged particle position and the decay vortex of the secondary particle very precisely. But now we are going for a sampling calorimeter where the silicon will form the active layer, and then you have the the copper or tungsten passive layer. So it's a so-called sampling calorimeter. And in this case, you are going to such an exceedingly high granularity, so that you are essentially doing the tomography of the whole shower. What is shower? When you collide high energy proton is lots of particle coming out of this collision, and they give lots of particle, like you can have electromagnetic shower, which is basically by electron and photon. You can have hadronic shower by this so-called quark and gluon, all these mesons and the baryons that are coming out of that. So what you see when you go to the high luminosity LSC, that will be you're talking of something like 140 to 200 what we call additional interaction or so-called pileup. And over a length scale of few centimeters, what you have to do, you have to do physics. First, you have to find out this particle, that whatever decay process you are saying, or whatever process you are saying, from which of these 140 interaction points that you are getting that particle. So that is the group. And then second thing, you see that how messy the environment is. So in order to do science in such a messy environment, high granularity calorimeter will play a decisive role. And in particular, you see this depiction here on the left-hand side, that you are talking of this so-called the Higgs boson production through this vector boson fusion. So you have a quark coming from one proton, another quark coming from the counter-rotating proton. Both of them are giving two vector bosons, W or Z boson, and they are fused together to give the Higgs boson. And then the Higgs decays to two protons. All right. So now you see in this particular, this is of course a simulation where you have 140 pileup events are superimposed. So you see that this is your vector boson fusion jet, the signature of this jet, and then the photon, and this is how, you know, it's kind of the whole jungle, you can say. There's lots of pile of it, and thanks to the information that you will achieve from the calorimeter, by you're able to really sort of reduce this kind of the background or the pile of hits and able to do your science. So at this stage, I will hand over the mic to Kamesh, because he will talk of more on the instrumentation part. And of course, this question on this part, if you have, I will come back towards the end. So I will request you to wait till the end of the seminar. Of course, you can ask in between, but let's hope that we will ask in the end.
Good evening, everybody. Now I'll talk about the Belle 2 silicon vertex detector. And here, particularly, if you see, this is the detector, and what we are concentrating on the VXT, which is consisting of the silicon PXT and as well as the SVD. And the particular PXT has 2 layers, which is very close to the interaction point, and SVD has 4 layers, which I will talk about that thing. But for this SVD, what we are using as active element is a double-sided silicon detector, strip detectors. And what is the main requirement of our VXT is that it is very because of this this electron-positron collision, which one is that electron at 7G and electron-positron at 4G. So a lot of after interaction, the rate will be very high. And other than this thing, so we need to have a spatial resolution, so which we can match with this silicon detector, and it is very radiation hard, is around 10 megarad, and we need to have the good tracking ability of this VXT. And not only these things, and we need to have the precise determination of the vertex position of the subatomic particles, and also the track position and movement of the charged particle. So what is there in the DSST is a simple PN junction diode, which is in the reverse bias mode operated. That's a basic principle. And here what we are using, we are doing it on a silicon wafer of 300 micron on 6-inch wafer. And this is the N-type bulb. We will take that thing. On that thing, we implant the P plus implantation. This is the direction of P plus, and N plus is on this direction. So both will be orthogonal to each other. And on that thing, to take the signal to the radio electronics, we are placing the AC coupling. So what we do is just in the P plus implantation, we put the silicon oxide layer, and on the top we will put the metal. Then we will connect it to the radio electronics. So similarly, we will do it on the N side also. So here, N side, other than N strips, we need to have the P stoppers to stop the electrons collected in the back side of this one. We need this system. And of course, we are connected in the reverse bias, so the holes will be to the P plus and electrons will be to the N plus to collect the signal with the radio electronics. And the layout of our SVD module, if you see, each ladder is consisting of the DSST along with the assorted electronics. Okay, so we have 4 layers: L3, L4, L5, and L6. And this is a rectangular sensor, which are here, and particularly we call it the back side here, and the central sensor, and the forward and trapezoidal sensor, which is here. Okay, and if you see the cutout of this SVD, this is the forward and the backward. It's angular acceptance is this one. The main purpose of this trapezoidal having this type of shape in the forward direction, to because of the energy difference in the collision, so the more particle will generate in the forward direction. So we would like to capture the particles in the direction in the forward. And these are the radiuses from the interaction point of these things, which is for L4 is 80. And these are the institutes participated in the assembly of the ladders. Particularly, we prepared the L4 and these piece of philosophy forward and backward. Forward means this assembly is done by piece of philosophy. So it consists of all this thing, particularly each sensor and its radio electronics. This is the only things we have on this ladder, each ladder. And this is the 3D model of this one, and which consisting of this is having the double-sided sensor here, and here this is a rectangle. These two are rectangle here, and particularly this one, this electronics is here. Particularly the central one, we are having the origami concept. We would like to take the signal as near to the sensor and take the signal out from this side. So that's why what we have done is the concept of origami, placing of the readout chips on the sensor. That's why we call it as origami concept. It's called origami module for it. And the forward sensors along with the electrons are shown here. So some of the details of the sensors and their strips, particularly our because of the we have a high resolution. So because the gap between backward and central sensor is 120 microns, and forward and the central sensor particular is around 394. The number of strips here is mentioned here. The P side 768 and back N side is 512. And in these things we already introduced some intermediate strips which we are not reading, but it will be useful for charge shares of the signal. And the pitch, which will affect the resolution of this pitch, which will reach the spatial resolution. And this is some similar number of these P side strips and N side strips here also on the observer sensor here. And what are the components other than this sensor and radio electronics? We have some other components which I will explain my during the assembly of process. The ribs are there, of course, forward backward I told you, and the ribs which is made of carbon fiber, which is lightweight but very stiff, and we need to have the low metal budget near interaction point, and some of the forward and backward elements are there. On that thing we like to place the hybrid boards. And the Kokeshi pins, these two pins are used as a reference pins and try to place on the end mounts. That's why we use this thing. And prism drive, particularly we place this prism drive in the forward side there, so that if you want to, while placing, if you want to have fine adjustment in the forward side, you can use this prism drive for adjustment. And the APV cards, which is mainly to place on the APV chips, but they are to take the heat from the APV chips. And the AREX, and which is act as the insulator, which I'll tell you. And the Origami is a readout chip, and the CO2, which will place in the CO2 pipe on the APV chips, so that we will remove the heat from that one. And the head shape, this is the purpose of the head shape. And how to assemble this one? So what we need is need a clean room, and the expensive equipment we need it. And we need to place the components precisely. And what we need is the mechanical fixtures, we call it jigs, to place these components. And to prepare the jigs, we need to have the 3D models and followed by 2D, and jigs we have to produce. And once the jigs produced, we need to measure under same what is the quality of the thing, and if needed, we should fine tune it. Once the jigs are ready, what we need is there is two components, and is gluing and as for wirebonding. I will discuss on that thing. And once these two are ready, then what we need to do, how accurately we assemble the components, a ladder particularly, so which we measure with the CMM and followed with the electrical test, how good is our electrical output from the ladder. So these are the particularly these sticks. I myself only learned this Autodesk event at 2012, and all the designs are done from the scratch, and these are some of the 3D models I'm showing here. And approximately, because of this assembly, a lot of jigs are needed for the assembly. Approximately 30 numbers are there. Some of the jigs are produced here, and we are showing the picture here. And this material what used here is aluminum alloy 6061 and the polyester. And particularly this wherever the sensor and the hybrid board, wherever you place it, normally you use this type of materials, polyester materials, so that you should not spoil in the sensor. Hybrid boards. So for each jig is meant for its own application. And not only that thing, we have this wirebonding mission and gluing mission. So not only that, those six, and here the particularly this wirebonder, when you receive these things, the size of working area is very small, around this much only, because it's meant for 6 inch. When it came, it is only this much area only. I can assemble it's around 200 by 200 area. But because of my assembly bench is bigger, which I want to accommodate my assembly bench here, which is have the 650 mm of the length. So then I made the modification of this assembly here, and we place this thing. Similarly, the gluing rod. So we need to place our jigs accurately. This repeatability is needed for each application. So we place the modified the base plate here, and also put the pins. Here some alignment pins are there for each jig. So every time we put back and remove, we should get the same position. So that's what we align all the pins such that all the jigs, whatever the jigs you place it, it's perfectly aligned with the gluing rod or the jig. And the tolerances what we achieved was particularly length of rods is very good, and particularly the small jigs Also very good, you can say. The 70 microns is quite good. And particularly the flatness of the large jigs because of the length. So normally we have more deformation of jigs.
So this tolerance of 40 micron is over what length?
So these are the particular length of the rods are not much. This is 10 centimeters. Yeah. I will show the I will show the length. Yeah. And all the jigs and CMM are produced in our workshop. Yeah. So why we assemble? We assemble this thing in IPMU, University of Tokyo, and then we have myself L4 and the L6. L6 also part of assembled by the University of Tokyo. We assemble. The reason doing here is that the particularly we have the import restriction of the readout chips. We cannot import the chips to India, so there is a lot of restrictions so that we cannot assemble in India and we have some funding issues on that. And the advantage of this thing here doing here is the sharing of resources, and we have good environment is there to assemble it. And you see, because the delicacy, we need to transport the layers to the KEK where we will have installed those things. These are the all advantages here of doing here. Yes, other than these things, now I'm almost entering to the layer assembly. So these are the steps involved in the assembly of my ladder. Just to see something, this is sensor picture after and read the assembly and some of the half ladder. We call it depending upon the status, we'll call it these things. And what we need the equipment. So what we have from TIFR is the just wire bonder and the microscope. And with that thing, along with our manpower and the other these things, we could able to do it. And what we are sharing with the IPMU, so these are all IPMU property. So this this one and this one is the most expensive instrument. This is the CMM mission, coordinating engineering mission, where we will place our jigs, the assembled ladder measure its precision levels. And this is a gluing rover, which will perform the gluing, and it's a pull tester. It's mainly useful for after performing wire bond. If I want to know the strength of the bonded wire, so we use this pull tester to know the strength of wire. Before going to the assembly, just I'll discuss about the gluing and assembly. And this is a robot used, and these are I told you the alignment pins. And this is particularly whatever we are using is the Japanese version. So mostly the teaching content and the program is assembly language. Some part is in Japan and some part in English. So we could able to because with the help of the Japanese colleagues, we could able to program this mission. And the main important factor is that along with this mission, we have placed some XYZ stage, which is very much essential for our this thing. Along with the camera, to move the position of this strip as position of the tip, which is very important for us. And we develop the programs for different applications here, which I'll show in the next slides. And how we are perform the gluing. So normally we are using the 2011 Heraldic is there, which is using the syringe, and after that we'll centrifuge here with these things, and we'll place at this XYZ stage, and then we'll see the position of this thing. This is what we'll do. The jet position is a cross axis is there, and we'll try to adjust the jet position. And here is the XY position. You can see so that exactly. So the main important of this gluing is that particularly more glue, it will go on the pads, which is not allowed. And less glue, well, it's a problem for me to perform the wire bonding. And the bubbles will form in the glue, so that is also not allowed. So bubbles that I cannot perform any bonding. So these are the things, important factors. So we have optimized all the speed and distance, height of the syringe to get the figures.
So how particularly you handle the bubbles?
How particularly is mostly. Yeah, forward back and just go back and then forward, yeah.
Always we come out of full screen and then go to that slide.
Yeah. Yeah, can you repeat the question?
Yeah, so question was how do you take care of the bubbles?
Yeah, so that's why we use this centrifuge. Centrifuge, then we will rotate it, this speed for particularly 7 minutes. Then because of the centrifuge, the bubble is created. So these are the glue pattern of the different these things. Particularly wherever the bonding pads are there, that's very crucial for me. Particularly here is the location feature after bonding here, and here we are using this extreme end where this is the place which is very critical. Plus this particularly glue also when it if it stick to the jig is very big problem. It disrupts my whole assembly procedure. And particularly here is the one, particularly here is the and this is non-critical, but it is important for this area. And wire bonding, yes, we have mission, and I am using this 25 micron wire. We are using aluminum wire, and particularly this is a tool we call it. On that thing, we have this 38 micron hole will be there, on that thing will glue the wire. This is the procedure to perform the wire bonding. What it will do is that first it will go to the place where you want to bond. Then it will apply the US power, then it will go to the next bond, next location, and again same apply the power, then it will that's what it does here. And if I wanted to know the how much is the strength of each location, what we do is that particularly you have to do it on the test samples, not on the actuals. So these are some of the parameters which I will apply here, and these are the when I use this test it here like this, where some of these things are we receive the force, which is the average comes to 11. It's very good for us. Normally, what we need is 8 grams, very good. And normally, we do this for 100 samples. And this is the sensor feature adapter. And what after dispensing the glue on the feature adapter, so we place it on the sensor. Then we wait for 1 day. Then it will be cured. And then we go for the wire bonding. So these are the places where we perform first because the 2 columns are this. First, we perform the inner row. We call it this. Then later we perform the outer. So this is the number of bonds I will perform here. And the reverse assembly, as I told you, this is meant for placing the sensor on these ribs. So this is some setup we have, so that this is a prism by which I am telling you, which you can adjust it to a prism here. And after that, of course, here is some gluing process also there. It's not critical. And after this is the things where we can base our sensors. Half ladder, before going to half ladder, what we do is whatever the the SPA, whatever then we place it upside down here. Now the bond pads are the downside, we have to take care. After that, what we do is with the forward and backward, the assemblies are there. What we do once it comes here, we'll test it and pick up and place SFW and SPW. So this is a lot of procedure is that I'm just taking. And once these are all sensors in the assembly bench, now this whole assembly will move to the CMM. There will align the position of each sensor with respect to the design patch. So for that thing, what we have some 2 reference holes are there, which will be used as a reference so that the positions of the sensors are as per our requirement. Once this thing is done, then we need to pick up the forward and backward sensors and try to place it under this. There is a procedure. So here the one jig is that particular slant jig we call it. This is a slant jig is the pick up in the horizontal, but place it in some angle. This is what we require here. And these are the these are the end modes. On that thing, you place some of the seal pad and keratin in the bottom side there. Here. So I will explain this. And this is the setup before placing of the forward and backward. And we have the ribs and the stand-ups are there, which you can see here. On this stand-up, we will place the glue. Normally, this glue will place it by hand. We don't have any option here. And particularly the forward side, as I told you, so we can just backward one, you can directly place it, but forward side, once you place it, there is a chance that these feathers will touch the animals, so that it will spoil the bond pads. Particularly these sensors, they have the wire bonds on the both top and as well as bottom, so you should take care of those things. Particularly these pads, particularly if you move in the Z direction, it doesn't touch the wire bonds, but once you do in the horizontal movement, there's a chance that it is test the errors. So here, one of these things, once try to adjust the hybrid board, so it literally moves. This is also not good for us. So we observe this thing because one of the ladder we have some issue which shows that it's the deviation of the particular one corner as related to more as expected. Then we try to find out the issues. Then once this what placing of the forward and backwards, backward no issue. And this forward, you have to place it some angle. Normally, what is the degree is 11.9 degrees. And here, after this thing, the glue after glue curing, we need to place the APV guard. So this is the APV guard is very critical because the wire bonds are there at the top as well as the bottom. You have to take care of the both the sides. You have to align this hybrid board to these holes here, which is hole here, and we will place. This is the APV guard. This is the setup which we have done it. And here we will place one hole is there. We will put some circular rod here. Through that thing, we will place this color. So this is the after line. After placing these things, this is the what you can see here. So it's very close to wire bonds on the top as well as the bottom also. You have to take care. So once you align these things, you can see the picture here. So this kerata is around this length is around 8 mm. So this is the 4 mm. So within the 2 mm, you can have this wire bonds of the. Similarly, we have the back side also. Similarly, and particularly here back side are the same thing, and we have the two rods little bit different, and we try to place it the variety cards here here from the top. So not only this, particularly it has a limited space is there. You have to hold this thing and try to remove this rod and try to put the screws, and little bit complexity also there. Putting and removing the screws also. Then this is the setup of the completion of our APV cards. And this is the after removing our forward and backward. So this is what the rods here. These are the rods which we have placed. This is the length. So these after removing. This is the half flat is there. Okay, my half flat. Now once the half flat is there, these are the two, but the central part is there. What we do is the central part. So what we have to do is this on the central one, we need to place ARX. Normally, as usual, we have the pickup and dispenser we want to place it, and then glue curing. After that, again, the similar to the Origami module also the same. And after placing the Origami, you can see the sensor and ARX and things. Then normally this is around height of around 1.2 mm. And we need to perform the wire bonding here. Once this thing is done, we perform the wire bonding. So roughly we perform 5 hours. The critical during the wire bonding at this point is that particularly after placing here, we have normally when you want to perform wire bonding, you need a proper support and glue. Particularly at this corner here, these corners at the edge of these corners, we have no proper support. We need to have the no proper support. Because of that thing, there is a difficulty I face during the performing wire bonding. That's one part. And another part is that after in some APV to this thing, when you perform the wire bonding, there is a chance that these wire bonds will get shorter. So that particularly the pitch is this 88 micron. So particularly I need to use this 14 micron probe tip is there, which I have to go there and try to remove. Otherwise, the same if it is shorting, so the two channels are not useful for the distance. So normally, whenever we observe these things, then we should do this. And this is one of the difficult job we have to do under microscope to remove these wire bonds. There is a chance that it can break and make. So, but the area of rebonding is very difficult in this things. Here we have space, but here the sensor is a difficult space. And dispensing the glue, whatever the assembly page, what we have, the whole assembly we place in the ring rubber only to dispense 2 lines here. Particularly the pitch adapters which are flexible, so that we need some support here. So we support it here, and after that we dispense here. So that can dispense the glue perfectly. And the other part is the wrapping. So what we do is all wire bonds are there. The glue was dispensed. This fellow has to be wrapped above these things so that we can glue the things here. So this is also one of the toughest jobs. So that we have everything you have to do it under microscope. And during the wrapping, you can see because even though we are holding the vacuum, it doesn't hold perfectly because of the curvature of these things. So this is the after assembly. You can see the wire bonds. We are not spoiling any. It's not spoil any wire bonds while wrapping up this one. And how accurately I place the glue. So as I told you, glue is the very important. This is the after wrapping. This is the glue condition of these things. It's, I can say it's very good for me. So as it's no spread on the patch, so I can perform the wirebonding here. And particularly here, because of the difficulty in the patch structure, they arranged it in 3 rows. And other than that thing, we performed all the wire bonds at different locations, which I can show here. But at the APV side, which you can see roughly protectives are there, we need to perform all 80 plus bias part transfer. So this is a origami. This is a place where I used to perform all the wire bonds here. And this is the final stage. Along with that, we have some test setup for checking the fiber optic. We have some slot is there, which will be this fiber optic will be used to measure the APV chips. Where some sensors will be placed in the fiber optics, which will measure the APV temperatures. So we have this fiber slot. And after that, after checking, then we need to place this origami part on the center. So which we are done. After that placing, then we need to place the CO2 clips, which will take the pipe, CO2 pipe will be there on the real assembly. So this is my ladder is ready for testing. And how I will test my ladder, how accurate ladder. So we need to perform this slant angle, tilt and rotation angle. So what we have is that each sensor, 4 corners, we have the 4 F marks are there. So we'll try to measure the F marks and try to measure its center. And we'll make a diagonal and we will make this is the center of the gravity point here. So that point will use just a measurement with respect to this. This is what our displacement, what you're supposed to be given the limitations are 150 micron in X5 and Z 250. And the slant angle is 11.9. So what is the design what we achieve? That's we have a very good results, and we similar results are we achieved in our results. Once the mechanical is okay, then we need to test the electrical. So here we show whether there is no shorts, open, noise. You can see everything here. This is some setup which you have. So there is not only these things, prepared a manual and other things so that for each and every step we will follow, because our sequence is sequential order. We cannot go back and do something, then we can rectify now. So that is not possible. Yes, if something goes bad, we have to just simply throw the things. Okay, these are checkups and these are the review. All our jigs and letters are reviewed by the expert people, so that we have given the grades to these class A letters. And before putting on the final SVD, so we are placing the Gagan at the stage, and this is the setup to place your ladder. And this is after L4 is installed, and this is all ladders are installed. This is a picture for all ladders are installed. Issues, of course, the first ladder itself has a problem, because once I have done everything, but as per the requirement, it is not drawing any current. So I took some time to find the open in the Origami module, and we solved it. But after that, again, it's not getting as per our requirement. The sensor was tested for like this. It's supposed to be break more than 200, but it's breaking because one of the wire bonds has spin hole. So because of that thing, it is misbehaving. So fortunately, this particular answer which is accessible to us, so that we can remove the spin holes. And the design issue. So if you see, this is the L5 and compare it, this is the picture of the L5 which you can see here. The sensor and pitch adapters, they are very smooth here, particularly the L4 we have a lot of tension that we have here. And this is the sensor with glue, which you can see here before placing on the ribs. And after placing on the ribs, you can see the shape, which is literally. Why I'm showing this thing is here because of this one. So during the particularly the 4th ladder, I have the issues there. I assembled everything and found that this was really built up the sensor. So which I cannot do anything here. It's point of we have to discard this ladder. And after that, there is only the full assembled ladder. Now it is the half ladder. So this is the half ladder. Once we have prepared the half ladder, we found that it happened once again. Okay, and half ladder. So now we have to discard this one. So after to avoid this feel of reinforcement of mylar sheet was done. See this what we have done here. Okay, then after that we because of the issue of the half ladder has been as a problem, I cannot continue my assembly. So what you have to do, this is a half ladder problem. So if I wanted to continue my assembly, I have to remove this origami from the assembly bench, then only I can do it. So at this stage, we kept the jig in the ITM view, then I came here and designed, produced, and tested, and gone there. This is jig there, gone there, and we have produced it. And this is only one time. You cannot do the repetition, just do it. No, do it to take only one time and places, which you have done successfully. Yes, no issue. And the second kill off, again it happened. So even though after reinforcement, it has done one more time. So at that point of time, we are not only in L4, they have observed in L6 also. So now they have done 2 more L6 there. So what is this? And of course, I also discarded this half ladder. And the precaution is that instead of the thing, just you prepare the half ladder and keep it as that. If something comes up with time, then you can take care of that. And remove the wire bonds of suspicious pinholes because our letters of there some things are suspicious, so then we could able to remove particular some of the problematic ones. And some of the one recently some of the noisy strips are there, particularly one of the due to the AP, so that we cannot continue that one. So which is normally it is less than 1% is allowed, so we will discard this one. And this is the picture of assembly of this thing L4 and L6 and with team, and during the assembly, our TIFR staff and IIT Chennai students are there, and particularly for installation, IIT Hyderabad also wanted to. And HGCAL, as already told the main importance. So what we need is the hydronautical element. What we need is a low cost, active area material, and radiation tolerant, on detector, high-end bandwidth, and other things are there. So this is largely silicon-based color sample. That's what we are planning to do here. So the main requirement here is the P-type DC coupled. We are using whatever our well-to we are using AC coupled. Here is DC coupled, and this.
You have 6 more slides.
Yes.
So I just thought.
Oh, because the DC coupled is very easy to manufacture. Less processing in the DC. And we use the N-type 300 microns and the hexagonal structure used so that we can utilize the area of the sensor. And what here is the 8-inch wafers are preferred because so that we want to cover. Cost per area is cheaper here. And of course, because of the position of the radiation, not position, because of the radiation effects, we have a different sensor thickness are used. Near to interaction, near to interaction point is 120, then as the distance increases, we use these other thickness of wafers here. And particularly total, these are very high volume, and particularly what we need to have to produce, we are planning to produce 5K silicon modules here out of these 2 years, and our plan is to produce around 15 modules per day. And here the 2 types are there, high density, low density. Right now we are only concentrating on this low density modules. These are these things. These are also has a same procedure as a gluing and wire bonding other things and process placing. And plus here we have after this thing encapsulation is the one which they wanted to incorporate here. So the encapsulation is that putting some silver on the upper part of the wire bonding. And there are 4 you can say base plate, kept on silicon and PC. All the reload come from the PC. Okay. This is some test module. So particularly here is that wherever our performance is our wire bonding and is linear wire bonding, 1-to-1. But here is that 120 degrees. I have to rotate the bond head and try to perform the wire bonds here. As of now, here TIFR would like to do these things. So as of that, we have instruments here. Plus on the way we need to plan to buy the so that it can mainly mass production. And wire bonding studies I perform on this thing because my wire bond is the 6-inch wafer, so the 8-inch wafer. So then we made it some dummy PCB, and that thing I could not do it during the work. So 2 times I have to perform that. And these are the particularly the stepped hole, not only on the top of the surface to top of the surface, mostly what the stepped hole. Inside the hole, we have 2 holes are there from that thing from here to here. I have to perform the wire bonds. And this is a dummy module which is to perform some test. on this also. So for to have, I suppose this one, what I have done is that design some jigs which suitable to example without gallery, because right now is on the way. We are in the process of we already placed the order for that one. So before that, we like to pay the do the mock-up study with the jigs. So we are clear. I designed some jigs, and on that you can see the blue pattern here, and these sensors, and these two are grouped together, and the blue thickness watch HU is around 60 micron. And this is the PCB pickup, which can I use these jigs to pick up. This is the pickup from the multiple. So you can see the pickup PCB, and this is the blue pattern performed on the sensor. See here, and after this blue pattern, which replace this pickup, you can place it on the sensor. So what we found that particularly these locations are the sector location. There's a blue spread is there, which is not good for us. So of course, it's the thickness which is here. So what this is the blue spread here. This is inside. Blue spread. So what we will optimize our parameters, bonding and the blue one. This is what the cloud structure where we have very close close holes are there. Things. And yes, after this things we got very good results. And not only that thing, after this thing we perform the wirebonding and then encapsulation studies also, which we are supposed to do on the actual models. We already perform all the tests. And the main galleries, this is what we are looking for this, so that we can have the more models can be assembled and these things. So once the models are there, we have to place it in a cassettes so that you can. This is the where you can see like 2-3 models. They will place it on the top. They will place another PCB so that this connection is there from this. And this is what we call cassette, and they, of course these are and the distribution of the cassettes. And particularly here, the high density, we have the 120, and the other places we have the low density models. This is the value of both the end caps, which covers the 600 meters of the silicon, and the number of channels are very high. The summary, we are for the first time we are in more it's a high pressure detector, and we started from scratch, and we are at par with other people from Japan and European. And now the jigs were designed, produced, and fine-tuned here. And we are expertise in wirebonding, full testing, all this analysis and electrical test. Establish fine-tuning and assembly procedures, successfully built to install the production gear that has the value detector. And this is CMS as we started studying the prototype, and we performed some doing and wirebonding, and some studies are still going on that thing. I need to develop the jigs for the main gallery for the product for the mass production, and we need to be developed for the gallery for the mass production. Yeah, that's it.
Yeah. So so before we go to the questions from the Zoom guys, since people are present here, they get the first chance to ask. Any question here? Okay, fine. So
You don't realize your question.
Yes.
I just have one question. When you did the gluing for the bell, was there any time constraint that you have to do within some time frame?
Gluing? No. Because we don't have to worry about the timing. So we have to worry about the assembly. Even if I take 1 day, 2 days, doesn't matter. Normally for my assembly of this thing, it takes 4 days. But normally I take another 2 days or 3 days continuous, 50 days the target. Even if delayed by 1 day or 2 days.
That is another added challenge for
So
the engineer.
because
That is why I asked.
we do it very slowly. We don't take in a hurry. Because it's a irreversible process. Anything to do it, I cannot go back and do anything. So we have to just do it.
So the group gluing was 24 hours. But then the thing is, since it is not done in TIFR, and these guys have to go to Japan, so they cannot go. There is some visa restriction and all this thing. They can at a time can spend that much of time. So you have to make proper planning that during that period, how many. So because you cannot do something, have and keep it there and then go after 1 month. So those things has to be done in a very planned and coordinated manner. So we always built in some contingency into our planning, so that that even if these things can go a little bit north and south, you can do that thing. And we used to have pretty much lots of video call back and forth on this discussion.
Okay. Any other question? Okay. Prabhakar, you can unmute yourself and ask, please.
Yeah. Yeah, thanks Gagan and Kamesh for a very nice talk. This is not a question, it is, I want to share some experience. While this ladder work was going on at IPMU, I had a chance to see it. Thanks to Kamesh, who took me inside the lab. I had to wear PP suits to go inside. Probably I did not stay more than half an hour. I felt very uncomfortable. I wonder how Kamesh et al, they are working hours together, even months. So apart from skills, it requires lots of patience, as I understand. Yeah, thanks, Kamesh. Yeah. So I have a question to Gagan. So basically regarding this W boson mass, as you might have heard very recently, so the W boson mass
Right.
is different from what was predicted by standard model.
Right.
This is with the CDF old data. CDF already closed. This is by, I think, Asutosh Kotwal.
Right.
So could you explain how it would affect the physics?
Right. So yeah, that's a very good question. So the question is, I mean, that all of you heard. So he's saying that the W boson, which was measured recently, is TIFR. Let's say what was the most precise measurement was from Large Electron Positron Collider at CERN. The combination of 4 experiments, the combined thing, and Prabhat's question is like, if this W boson mass is different than, then what kind of implication it can have, right? That was your question, right?
Yes, exactly.
So the question is, there is a, I showed in the first or second slide that you have there's so many particles and you measure their mass, and there are 3 particles, let's say, so I would say 4 particles. They are really critical in the sense, one is of course, the most critical to my mind is the top quark mass. Because when you go to so-called quantum correction higher order diagram, so you will have this the contribution for the top quark that comes in a quadratic way, and then you have the Higgs boson that appears, and that is a logarithmic dependence on the Higgs boson mass, and then you have this W and the G mass. So you put together all this in a so-called global electroweak field, you can see the cell consistency. So right now, the kind of difference that Prabhat you are saying, it is not something I would get excited. Like, let's say whatever difference there is finding on this versus whatever measurement we have from the top quark mass, as well as very very precise measurement of the Higgs boson. Again, from CMS experiment. I mean, if you see the single experiment, most precise measurement comes from CMS. If you put them together, I don't think we are at the stage where we'll get very excited that this is something. So yeah, but the story is like I was talking about when you related that flavor anomaly or other thing. We have quite a few, let's say, difference with respect to what you expect from standard model, but none of them have got to that level where we can say that here it is. I mean, so that is what we are looking forward to.
Okay. Yeah, thank you. Maybe I will stop here. Let others ask. Yeah.
Just want to add what Prabhat asked. Do you mind that I can say?
Yeah,
You can say. You can say.
Prabhat, can you hear Manoranjan?
Yeah.
Manoranjan, not so clearly. If you can.
Repeat the question. Yeah.
What I see is that you are talking about this about 7 sigma excess of W boson, right? So
Yeah, right now, yeah, this new result, which is different from the standard model by 7 sigma, right?
something like that. So what
Yeah.
is that it is very difficult to accommodate this 7 sigma from the standard model. So if you add more diagrams containing the particles beyond the standard model physics, then maybe it is possible. In this case, maybe the one example is the low supersymmetry with the very lowest particles that is favored, that can explain this extra 7 sigma. But it is too early to comment.
Okay.
Really, we need to see that what really they have done it so that they have got the 7 sigma excess in the WMS measurement, which was measured, I think, more than 25 years ago. And we need to understand this result first.
Okay.
And, just to add on that, one of the things when you are making some precision measurement, the systematic uncertainty is the key thing, right? And so there is this hadron versus electron machine, like there's quite a few things. Just to give you an example, in the stock work, we have reached a stage where adding more data is not going to help, because the statistical uncertainty, like, goes over 1 over square root of L of more data, but then the systematic part, that is sort of unless you find a new way to tackle that, your total uncertainty will remain pretty much unchanged. So in that context, like so this whatever measurement we have, we need to have independent like validation, and we have to see the systematics, all that thing that has been done. They need to be properly understood. So I will not get too excited right now. Well,
Okay.
yeah.
Yeah. All right. Yeah. Thank you.
Okay, any other question? I don't see any hands up from the Zoom audience. Okay, Rav has something to show
Sure, yes.
on the video.
Yeah,
So
yes, yes.
this is the video.
So this is mainly the bondings and other things. So you do a bell too.
So music was you wanted, or
Something.
I thought music was not there.
Yeah, music is not there. And this is for HGCAL model. 9 word bonds.
Actually, Zoom participants, we cannot see it, unfortunately.